Hi everyone, myself Dr. Binsi and I would like to welcome you all to the lecture series on crystal defects part 2. In previous lecture, we discussed in detail point defects which comes under stoichiometric defects. So today, we are going to discuss in detail non-stoichiometric defects. Before that, the compound in which the ratio of positive and negative ions present in the compound differs from that required by ideal chemical formula of the compound are called non-stoichiometric compounds. The defect in these compounds are called non-stoichiometric defects. Non-stoichiometric behavior is the most commonly found for transition metal compounds. It is also found for some lanthanides and acetinides. There are of two types depending upon whether positive ions are in excess or negative ions are in excess. These are also known as metal excess defects and metal deficiency defects respectively. Thus, two main divisions for non-stoichiometric defect, one is metal excess and another is metal deficiency. So let us discuss metal excess defect. In these defects, the positive ions are in excess. These may arise due to the following two ways. First one, anionic vacancies, and second one, presence of extra cation in interstitial sites. Coming to anionic vacancies, in this case, negative ions may be missing from their lattice sites, leaving holes in which the electron remain entrapped to maintain the electrical neutrality. This is shown in figure here. Evidently, there is an excess of positive ions although the crystal as a whole is electrically neutral. This type of defect is observed in those crystals which are likely to form Schottky defects. When alkali metal halide crystals are heated in the atmosphere of the alkali metal vapor, anion vacancies are produced. For example, when the crystals of NaCl are heated in the atmosphere of sodium vapor, the excess of sodium atoms are deposited on the surface of the crystal. The Cl- ions diffuse to the surface of the crystal and combine with Na atoms to give NaCl. In the process, there is loss of electrons by sodium atoms to form Na plus ions. The electrons thus produced by the ionization of the sodium atoms diffuse into the crystal and get trapped at the anion vacancies. The electrons trapped in anion vacancies are referred to as F centers. This is from a German word, Farbencenter, meaning color center. This impart yellow color to the crystal of NaCl. The color results by the excitation of these electrons when they absorb energy from the visible light falling on the crystal. Similarly, potassium in KCl makes the crystal appear violet or lilac, while the excess of lithium in LiCl makes the crystal appear pink. And this is the F center, that is E trapped in anionic vacancy here. Next, extra cations occupying interstitial sites. In this case, there are extra positive ions occupying interstitial sites to maintain electrical neutrality. This defect may be visualized as the loss of non-metal atoms which leave their electrons behind. The excess metal ions occupying in interstitial positions. This type of defect is found in crystals which are likely to develop Frankel defect. The most common example is ZNO, that is zinc oxide, which is in white in color at room temperature. On heating, it loses oxygen reversibly at high temperature and thus turns yellow in color, and the reaction is shown here, that is ZNO when we heat it gives Zn2 plus half O2 plus 2E minus. The excess Zn2 plus ions are trapped in interstitial sites and equal number of electrons are trapped in the neighboring interstitial sites to balance the electrical charge. This electron give rise to enhanced electrical conductivity and is shown here. Next, consequences of metal excess defects. The crystals with metal excess defects conduct electricity due to the presence of free electrons. However, the conductivity is very low because the number of free electrons is very small. Because of low conductivity as compared to conductivity of metals, these are called semiconductors. These compounds are also called N-type semiconductors. The crystals with metal excess defects are generally colored. For example, non-stoichiometric sodium chloride is yellow and non-stoichiometric potassium chloride is violet in color. Next, metal deficient defects. These defects occur when the crystal contains less number of positive ions than negative ions. These defects can arise due to the following two reasons. First one, cation deficiencies. Second one, extra anions occupying interstitial sites. Let us discuss cation vacancies. In some cases, the positive ions may be missing from their lattice sites. The extra negative charge may be balanced by some nearby metal ions acquiring two positive charges instead of one. This type of defect is possible in metals which show variable oxidation state. The common example of compounds having these defects are ferrous oxide and ferrous sulfide and also nickel oxide. In case of iron pyrites, that is FeS, 2 out of 3 ferrous ions in a lattice may be converted into Fe3 plus state and the third Fe2 plus ion may be missing from its lattice site. Therefore, the crystal contains Fe2 plus and Fe3 plus ions. This gives rise to exchange of electrons from Fe2 plus to Fe3 plus ions in which Fe2 plus changes to Fe3 plus and Fe3 plus changes to Fe2 plus ions. As a result, the crystal has a metallic luster. Because of the natural color of iron pyrites and metallic luster of some samples of minerals shine like gold and have been nicknamed as fool's gold. So the metal deficiency defect due to cationic vacancies is shown here. And this represents vacancy and this is Fe3 plus which shows dark in color and O2 and this is Fe, this is oxygen, this is Fe2 plus, this is Fe3 plus, this shows in dark in color and this is vacancy. Next, extra anions occupying interstitial site. In this, an extra anion is present in the interstitial position. The extra negative charge is balanced by one extra positive charge on the adjacent metal ion. Since anions are usually larger, it could not occupy an interstitial site. So such kind of defect is very rare because usually negative ions are of larger size and thus cannot easily fit into the interstitial site. And this, that is, extra ions occupying interstitial site, it is a theoretical concept. Anyway, this is the figure representing and this is the extra negative charge and it is balanced by the positive charge here. Thus, today we discussed non-stoichiometric defects and hope you all understand. Thank you.